Yeah, I hope everyone's back now and that you can hear me and everything. Everything's going well. Yeah, I hope everyone managed to install the package or open Binder or open Colab and just get the data set, the test notebook running. That's the most important thing for the next session. So here I'm just going to give a really kind of quick overview on each of the notebooks and what they cover within them and what you can play with, that sort of thing. And then I'll go on to GitHub and actually go through the notebooks in detail. So the first notebook is the test notebook, which I hope everyone's run now and making sure everything's running. Again, if you've got any errors with this or it throws up any errors on anything, just if you go onto the Slack where the sign up links on the events homepage, we can troubleshoot that with you. So yeah, the test notebook, just don't worry about too much about what's inside it. Just make sure everything runs. You don't get any errors. The dataset notebook, there's going to be two data sets that we're going to be using in the hands-on bit throughout the notebooks. There's a 2 moons data set, which Kacper had in his slides, which is the sort of like 2 half moons made up of 2 classes. And then there's the bikes data set, which is a data set that captures bike rentals over a certain period of time. So this notebook's just for loading the data sets and training some black box models on those data sets. There's the interpretal representation notebook, which goes over everything to do with interpretal representation and covers a lot of the things that Kacper spoke about for both data sets as well. So you get to see it in higher dimensions. By higher, I mean like 11 features in the bikes data set and low dimensions in the 2 moons data set where you can kind of visualize the difference between them. And then there's the data sampling notebook where we go over 4 types of data sampling. We've got normal sampling, truncated normal sampling, mix-up, and normal class discovery. And I think Kacper spoke about all these in his slides as well. And we'll go over some basic properties of using them on both the 2 moons dataset and the bikes dataset. And then there's the explanation generation notebook, which is where you put everything together and you generate explanations, either using something akin to Lime, using a linear regressor, or what Kacper mentioned is using a multi-output regression tree or a regression tree to generate your explanation. Okay, so now I'm going to go to the, I have it on a different slide, sorry. I'm going to go to the events page, and here's the link to the Jupyter Notebooks if you need a link to it. And I'm just going to open all of them so I can go through them with you. So this is the test notebook again. Each one of these notebooks has an opening Colab button and a launch Binder button, which will launch Binder for that notebook or open that exact notebook in Colab, in case you're wondering like how to open things. But yeah, don't worry about too much about the test notebook. Just make sure everything runs in it. We have the dataset notebook, which goes through loading the datasets and training the models. So again, we have these buttons for opening Colab and launching Binder. And we have some basic code at the top of every notebook that loads in the package for this tutorial. And this initialized Colab thing, which the code will only be called if the notebook's opening Colab. Again, like these are at the top of every notebook. So in this notebook, we're gonna go over loading in some simple 2D data in the 2 moons data set, which looks like this as shown. You've kind of got these 2 half crescents and their 2 classes. And we've also got separate test data. Yeah. And then we also have the bikes data set where you have these features here. So stuff like what season is it, what year is it, what month, whether it's a holiday, a weekday, a working day, what was the weather like, temperature, humidity, wind speed, all these things. And you try and predict into 3 classes where you have a low bike rental day, a medium bike rental day, and a high bike rental day. Originally, this was a regression data set, but we just kind of turned it into a classification data set. Just because it's a lot easier to generate explanations for and make those explanations clear. So yeah, we have low, which is between 0 and 4,000, medium between 4,000 and 6,000, and high between 6,000 and 9,000. And we try and predict which class each of the point lies in. And here's a quick plot of the class distribution of both the training set and the test data set. So we tried to create these splits so that there was no unbalanced data, but it's kind of hard to create 3 equal splits. And then we train 2 separate models on each of these data sets. And we're going to treat these as black box models, but they're different in the way that we have a random forest classifier, which is a probabilistic classifier. So it outputs sort of prediction probabilities. And then we have a SVM, which is a crisp or non-probabilistic classifier, which means it just spits out what class that point belongs to. And we're going to use these throughout these notebooks to show that you can handle both of them, and you just do slightly different things for each of them. So yeah, we just go through, we train a random forest classifier and a SVM on each of these data sets. So here's the code for training the bikes data set. And then we also have something where we store the values in Jupyter Notebook. This won't work on Binder or Colab, I think, but it should work on Binder, but it won't work, but it's mainly for local installs. And we don't use these in the other notebooks. It's for if you want to access the data set in a notebook that you create, we store all these. So we store the moons data, the classifier, and the crisp. And then for the bikes, we store the same. And you can access each of these if you do %store -r moons data dictionary, and that will load the moons data for you in whatever notebook you're working in. There's also this command. So for any of the functions, if you don't know what they do, you can do !, and then the function or class, and it will print the docstring for that function or class, which could be quite useful. It's like a quick way of looking at the documentation. So that's the datasets notebook. We then have a interpretable representation notebook where we've got the same boilerplate code for loading in everything, same Collab launch buttons. And we're looking at what Kacper spoke about in this presentation was different types of interpretable representations. So you have sort of discretization where you have something like this, where you're having a quartile discretization where you're just splitting the data into quartiles, and then you have sort of binary representations of this, which I think is shown later on. Yep. So this is sort of binary representation where blue encodes the x-axis, which is same as the star, which is the explanation point. Yellow encodes the y-axis, or the other way around, sorry. That is the same as the star. And then you can basically split these into 4 binary representations where you have 1, 1, 1, 0, 0, 1, and 0, 0. It's the same thing that Kacper spoke about. And yeah, we're just looking at this kind of steps through calculating purity for each of these weighted bins as well. So using Gini index purity to just try and see how faithful your interpretable representation is to your original data. And then we go through doing the same with tree-based discretization instead of quartile-based. So I think it's the exact same figure that Kacper used actually. That where we're using a tree to discretize our data instead of quartiles. And then we're going through the same thing of like, let's look at the Gini index for this. Let's look at the weighted purity. Kind of see the difference between each of the discretizers and the binarization. So it's the same thing. After we binarize the tree domain, we've got weighted purity, and we've got access to the actual decision tree classifier. And yeah, you're just seeing what different discretization does for the 2D data set, and it's quite easy to visualize it in 2D. In the bikes data set, it's a little bit harder, and I'm sure in any data set that you have, it won't be 2-dimensional. It'll be multi-dimensional or high-dimensional. So yeah, it's the same as the 2 moons data set. We're doing the same thing. We're doing quartile discretization. We're doing tree-based discretization, and we're just seeing the distributions. This is the distribution of prediction probabilities. So essentially in your data set, you don't want to have, in your sample data set, you don't want to have them all be one, because then the black box classifier is all just going to classify all your sample data as one class, and you won't really get a good representation of the decision boundary. So yeah, we're doing the same thing, Gini index, and yeah, looking at class counts, and then we start looking at the statistics for quartile discretization. So again, Gini index, things like that, and looking at the hyper rectangles, and in this case, you end up with most of the points in one hyper rectangle. I'm just kind of showing you code to just kind of try and see what's going on when you have quartile discretization or tree-based discretization. So yeah, we have the same thing, weighted purity for tree-based and things like that. So yeah, that's all to do with interpretable representations. Then we go into the data sampling notebook, which is again based off Kacper's slides. So you have 4 different data samplers. You have normal sampling, truncated normal sampling, mix-up, and normal class discovery. And there's a brief description about all of those and how they work in the notebook. But also, if you want a more in-depth explanation, you can go into the API reference in the documentation. And in the doc string for that class, there'll be a really in-depth description of each of the samplers, and also probably a link to a paper where it was introduced. So yeah, we're selecting certain instances to be sampled around. So we take 2 different points. We have a boundary point, which is where you're selecting a point that lies on the decision boundary for your black box classifier, and also a point that's far away from the decision boundary. Because how you sample definitely determines whether you're explaining a point that's close to a decision boundary or far away. Because when you're far away, it's a lot harder to be faithful to the local decision boundary, because the local decision boundary isn't exactly local. It's a little bit further away. So yeah, with the 2 moons data set, we can see all the different types of sampling around different points and what impact they have on the data you actually generate. So for here, you have the mean of the data set, the close to a decision boundary point, and the far point, and for normal sampling. And then we have the same for truncated normal sampling, which is where you have the min and max of the data set as kind of limits where the data can go. Then we do the same with mix-up, where you sample from a beta distribution, and you take 2 points, and the beta distribution determines where you sample between them. There's a better explanation of that in the documentation. And then we do the same with normal class discovery, which basically ensures that you have a certain percentage of your sample data is in every class. So it's a good way of finding a decision boundary and making sure that your sample data is somewhat balanced. Not balanced, but has a percentage of every class in it. And then yeah, we can do a comparison of all the classifiers, and you can kind of see what effect each of these samplers have. And yeah, you can run this on your own data. This is just like an example with a 2D data set. And then we can also do the same thing where we find the Gini index for the sample data and find out which one is more representative of the original data set. And then we go through sampling from interpretable representations. So sampling from quartile discretizers, where you have to sample from a Gaussian fit to each bin. And then we move on to the bikes data set, where we try and choose an instance that again is one that is the black box classifier is absolutely sure about, and one which the classifier is kind of sure about, but not really. And then we do the same thing. We test each of the samplers, and we visualize these bar plots show how much of each class is present in each of the sampled data. So if you look at the bottom left, the normal sampler for the far point has almost all of one class and very little of the others. So you found a decision boundary, but not really what that decision boundary looks like or anything like that. But again, it depends what you want your explanation to show. Depends on what you want these bar plots to look like. Then again, we look at the Gini index for this, and that is the data sampling notebook. And then we move on to the explanation generation notebook, which is all about the surrogate explainers that Kacper spoke about, going through something akin to Lime, where you have a linear explainer, and then something which implemented in Blimey, which is the tree surrogate explainer. So with surrogate explainers, you would need to kind of select an instance to be explained again. Here we select one close to the decision boundary, but inside the gray class. You have to sample data for a decision boundary. You have to sample data for a surrogate explainer. And I think here we just use the, we use mix-up here. So I think mix-up's probably a better sampler to use than something like normal for most things. Then we build an interpretable representation. Here we're just doing quartile based. And as you can see here, then we look at the weighted purity of both of these. And then we also do a tree-based interpretable representation where you fit a decision tree to your locally sampled points, which is shown here. And then we go into explanation generation where you use this discretization and you find some interpretable representation. And then you can weight your data for a linear classifier. You can either use Manhattan, Euclidean cosine, and then you can also have something like an exponential kernel if you want to weight closer points more than further points. So we just go through an example with that and how different distances can affect what your data is going to look like to your classifier, and also how different kernels can weight different data points to your classifier. So here we're just changing the parameter inside the exponential kernel and showing the difference with that. And it's quite a big difference. Like these parameters are quite important depending on what you want your explanation to show. And then we do the same with a tree-based classifier, tree-based surrogate, where you're weighting points differently to your tree. And then I think this is looking at the discretized data domain and seeing what that looks like. And then same again, looking at how the exponential kernel can change, how the parameters for a kernel can change what your data looks like, but this is all in the discretized data domain, not the original domain. And then we do the same thing again for the binarized data domain. And again, look at how the exponential kernel parameter can change what your data looks like in the binarized domain. And then we also look at explanation sparsity. So there's 3 different methods that we look at. There's the lasso path, forward selection, and highest weights. I think lasso path uses like something akin to lasso, where you try and find sparse features. Forward selection will iteratively add the features of highest importance to your classifier, and then highest weights just trains on all features and takes n highest weights or something like that. So yeah, we're looking at how all these things kind of affect the explanation that you generate and the sparsity of it. And then we also just look at tree-based explanations, where you can generate these decision trees and kind of what Kacper was talking about. You can generate counterfactuals intuitively by saying, if I change my x0 to be above this instead of below, I'll change class, or something like that. And then yeah, this is all about fitting a surrogate model. So this is fitting a linear regressor, and so something like Lime. I think Kacper actually had this exact figure in his slides, which is basically Lime implemented in our package. And this just gives you feature weights for each quartile, for the most important quartile, and same again for a different point. And then we use the tree-based explainer, where you can get feature importances, but you can also get these trees that are that are locally trained for the data point, and you can intuitively read off counterfactuals. And then we do the same thing with the bikes data set, which is a little bit more difficult because it's hard to visualize what's going on. But we also train like a Lime-like explainer, and we look at the purity, and we look at the Gini index for these. And we do the same thing with generation explanation, instance weighting, interpreter feature selection. We do all the same things that we do with the Tuman's data set, but with a bikes data set. And then we also get feature importances from this, and these are for quartiles based, so from a line-based explainer, and do the same thing for a tree-based explainer, and you end up with a nice decision tree that you can look at. And also, I think this is a rule fit explainer. Sorry, this was all a rule fit explainer, and down here is a tree-based surrogate, which is here. And then Kacper, we also go through a multi-output regression surrogate, which Kacper mentioned, where you train with, you don't train on the probabilities for one class as a target, you train on the probabilities for all classes as a target, and you try and regress all those probabilities. And then, yeah, then there's a nice summary about tabular Blimey Lime, because all of this is essentially already implemented in some classes that we made in the package, but we just want to step through and go through each of the independent modules that kind of make up this algorithm, or that you can interchange throughout. But yeah, there's some base ones that tabular Blimey tree that uses sort of mix up, and a tree explainer, and tabular Blimey Lime, which is our implementation of Lime essentially. And yeah, just make sure you reach out on Slack if you've got any questions about anything, and me and Kacper are on hand to answer any questions. So I'll just go back to the slides quickly, and yeah, there's a Slack where the registration's on the events homepage. If you join and ask any question, me and Kacper will definitely answer it. And yeah, next up is the active participation for, I think, 80 minutes, or I've gone over a little bit. So I think that is due to end at, active participation until 5:50 Central Time or 4:50 UK time. And then after that, Raul will be here to give a quick 10-minute summary and farewell. So yeah, if you have any questions, jump on Slack. I'll make sure to have the timer up on the screen so you can tell when the hands-on session's ending, and you come back for the summary and farewell. But yeah, thanks for listening.